So fine. What I am going to talk about today is choice of language, which connects physical stuff on one side and mathematical stuff on other side. So how does one go about doing this thing is, well, it's a map. So physical this is what I described in the previous lecture, that you need to do this. How this is done, it inherently depends on the type of the data and various kind of criterion. So call it this is at the back of our head, whatever it is, that where is the data coming from, what kind of thing is it, is light, whether it is sound, whether it is some picture, whether it is some text. All those kind of things will require some description in the mathematical language. We choose it accordingly, and then what do you want to do with that data? So you have a particular task which will be implemented by some kind of transformations, and what are the transformations needed will be encoded in the mathematical framework which we want to construct. So that is also sort of implicit, that you need to look at it. You just don't construct a language in a blank space. You look at the problem you are trying to solve. Now the third thing which I mentioned last time, that there is always a question of optimization, in a sense that you have to both minimize errors and minimize resources. This is a kind of trade-off. Not necessarily the best you can do over here, you may not be able to do that well over there. And this also I gave examples in the last lecture, that you try to minimize error, you add up all kind of redundancies, and that requires more resources. Or if you want to cut down on resources, you have to remove all the redundancies, and then the error probability goes up. So you have, that's a trade-off. So actually and now we try to put these things together explicitly. Okay, so what does, I will look at this criteria individually. What does minimization of error mean that unwanted noise has to be separated from genuine signal. This is just, we understand noise we cannot eliminate. It is what you call part of any physical system. There will always be fluctuations. They take various forms, and depending on the form, you can address those things differently. But the most common example is just thermal fluctuations, which is present whether you like it or not, and it's part of thermodynamics. That there will be fluctuations in any physical system, and the task is to protect against those fluctuations. There is a signal which you want to tackle, and this has a very interesting solution, that you somehow need to separate the scale at which the noise occurs from the scale where the signal is present. If you manage to do that, then you can take one of them out and keep the other one. And the first step in that aim is to digitize. It essentially separates the scale of the noise from the scale of the signal in some particular sense. So what does it do is small fluctuations are interpreted as noise, and large changes are considered genuine transformations. What do you mean by small and large is subjective. It depends on various kind of design parameters, but this is what you do to separate the scales. And then if the small fluctuations are there, small means there will be various digits, and the separation between the digit will give you the parameter small with respect to the separation of the digits. Whatever the digits are represented in some physical properties. So the physical property changes by a small amount. You count it as a noise. Changes by large amount. You count it as a genuine transformation. I gave earlier examples of currents and voltage in circuits. You assign certain values like 0 and 1 to particular intervals of the voltages and currents. If they fluctuate by a small amount, then the value of 0 and 1 doesn't change, but they change by large amount. You consider it a genuine transformation, and all the job is to keep the interval of 0 separate from interval from 1. That is a digitization process. Not the whole continuous values of voltages and currents are available, but only certain subsets are assigned values. So this is how you separate the scales, and if you are able to do that, then you can give a mathematical proof that you can construct a system which is fault tolerant. So all these small noises may keep on occurring, but they do not destroy the computation which you are doing. And it's buried inside all our computers, whatever we use as electronic circuits. The intervals are separated, what is off and what is on is quite distinct. There are voltage fluctuations, thermal fluctuations, all those things are present, but our computer keeps on running, doesn't crash. Once in a while it can happen that there may be a very large fluctuation coming from the noise, and then the computer will crash. This happens, for example, when there are energetic cosmic rays. It comes with very high energy and they disturb the voltages, and then the computer will give up. The program will crash, or sometimes the whole machine will shut down, but those things are rare. So that is a purpose, that you make these large fluctuations or large unwanted contribution to noise rare enough, and if you do that, then you have a fault tolerant paradigm. And all our computers which we want to design, we want to take in this particular region, that yes, there are going to be fluctuations, but I still want to carry out the calculation in presence of fluctuation. The second thing which is useful is that only bounded in a practical application, you do not need numbers with arbitrarily large precision. You say that this system which I have built is working with an error 1 part in 1,000, that's fine. You want to make it 1 part in a million, fine, but whatever it is not 0. Okay. And that is a crucial point, that is called a bounded error set of results, and these two things go together. Okay. You set up a system that it will give results with a certain bounded error, and then with that kind of a target, it will be fault tolerant. You are never going to look for exact mathematical identities in a practical computation. And even in our present computers, you calculate things, but it's some 32-bit machine. It produces 32 bits. It's not producing a real number which will keep on going for arbitrarily large number of bits. You don't need that. And that is a part of the process of particular digitization. Certain accuracy, you are happy with that, and you do the work. You can increase the accuracy for some specific task, but it's never going to be arbitrarily close to 0. Okay. And third thing which happens, which is actually very important, that the possibilities that can be explored with discrete values are This is a automatic consequence of digitization, but it's a very important consequence. For example, let me say that I have only 3 digits, each one going from 0 to 9. How many possibilities it can cover? It is 10 to the power 3. Okay. So you have some number of variables, but they are all independent. And the total number of possibilities is the number of possibilities for the first variable times the number of possibilities for the second one times the possibility of the third one, and I can do that because everything is discrete. And this kind of conversion, that you can get a exponentially large access to lot of possibilities by using only a small number of variables, is something which will occur over and over again throughout the theory of computation. You are looking for such situations that you want an exponential advantage by putting in only a polynomial effort. This is a very well-known criterion for defining a complexity of a computation. So it goes back to this second part, that you are somehow managing to cover lots of possibility with small amount of resources. So the digitization we arrive at by minimizing the error, but it helps in the other part as well. There is a another consequence, or not consequence, property of nature, which turns out to be useful in the digitization, that you look at any physical system at smaller and smaller size, things automatically turn discrete. Whether you like it or not, or whether you want it or not. You look at a continuous fluid or some solid, whatever it is, you can describe it as a smooth material in the classical language. You go down, it will turn into crystals and atoms, it discretized. Why so, we don't know, but it's there. You look at energies of various materials, it's fine, you can describe it in classical physics as some continuous variable. You go down to the atoms and molecules, the energies become discrete. It's part of quantum theory in a certain way, but things are there. So discretization is buried in the physical devices automatically, and that helps. You can turn the space discrete, you can turn the energy discrete, you can think about all the physical components like atoms, they are all discrete, there are only so many different possibilities, and that is a part of nature which helps. So in some sense, and in the same way that So we are turning things on our heads compared to how we learn things in, well, our schools or in educational system in general. You talk about continuum system, you do all calculus, differential equations, etc. first before coming across quantum physics. But the reality is the other way around. The underlying stuff is actually discrete. Integers are more important than real numbers. You have to look at all the kind of classical equations using continuous variables from coming from something which is more fundamental where the variables are discretely like integers. And that's actually a different way of thinking, and I'm just emphasizing that what is more fundamental is the discrete stuff and not the continuous one. So we have to not worry about many things, even though we write down a lot of equations or the whole calculus considered a very powerful part of mathematics. We are not going to really require it. We'll use it when needed, but the more fundamental stuff is just discrete mathematics of linear algebra using some vectors and matrices of some finite dimension. And this is means in some sense of important way which one should think about even while learning these aspects of physics, starting from whatever school or college, wherever you come across. Put more emphasis on the discrete stuff first and worry about the continuum later as an approximation. We learn the other way around. We take the continuum to be fundamental and then try to discretize and define a derivative and things like that by separating intervals. But that's not the case. Should look at the things in the opposite sense. And it requires some amount of training, etc., but it's important to keep it in mind. So now I will give the second stuff. What do you need to do by minimize resources? One stuff I already said that you want to keep the number of components small, but you want to explore large number of possibilities. Okay. That is well, it's so when you have only a small number of things, this second part kind of happens automatically. There's only so many things you can do. And those operations will look simple, nothing complicated. But by putting them together in some particular manner, you keep this thing versatile. Lots of possibilities can be covered, and the question is, can we construct a framework of this particular type. And we have lots of examples which will actually illustrations then before going to a more mathematical structure. One of them is a miniaturization. We continuously see things becoming smaller and smaller. Okay. In particular, in semiconductor industry, we have seen it drastically happening. Why? Because it's somehow reducing the resources which you need to solve the same problem. Also, it happens that you also miniaturize so that the number of components, whatever they are very small. And you don't deal with a large number of components. If you look at a computer chip, the ultimately bottom level, there are only few things you can do, nothing more complicated than that. But by putting them together, you create a large number of possibilities at the top level, and that kind of helps in managing the resources and covering a large number of possibilities. And there is a mathematical definitions one can give together with it, but this miniaturization but it again you have to keep in mind these errors. One thing which automatically happens with miniaturization is the things become more sensitive to noise. A big thing will be kind of inert stuff, it will stay put, but you make it small and small, the fluctuations try to disturb it more and more, and then it will be again a trade-off. How far you can go without the noise being under control or not. And that is a part of the process. And other thing which you can do is very commonly seen. What do you do when your computer disk becomes full? Zip the file. First thing to try out. Why? You are not losing anything, but you are reducing the resources. How is it done? Well, there is a lot of unnecessary stuff in the data, and somehow the algorithms are smart enough to take it out and compress the whole thing. And this is actually the way our practical languages are. They are not efficient at all. There is a lot of redundancy which is there. You play around with it quite a lot. When you are, say, these days writing messages on mobile, you don't write full English sentences, you write some SMS. I see you, so then I see and you, 3 letters are enough, and why do I have to write the whole sentence? That is the kind of stuff which happens. You compress the data without losing the information. But what happens that you have compressed the data, then if something is lost in that remaining data, the penalty you have to pay for the error is large. It's like one of the best compressed languages are just a number system. Okay? Every digit has its meaning. Okay? There is no redundancy. If you have a 10-digit number for somebody's mobile, you type 1 digit wrong, says wrong number. Doesn't do its job. So you have actually compressed the system as much as you can. You removed all the redundancy, but then the penalty for the error becomes large. If you have repetitions, well, you are adding unnecessary stuff, but then if something is deleted, you can recover from whatever remains. And this is a trade-off which is there, and you have to keep that in mind, that yes, you can do it, but then you have to worry about under what circumstances you would like to do it. And it just compressing the data just removes all kind of correlations which are unnecessary, and as I said, gives a number system is fully versatile in sense that there are no correlations. I can write one digit, and the next digit which will come, it can be anything. There is no restriction. But if you are writing a text, then you say that I will write a what you call a consonant. Very likely the next letter will be a vowel. Not 100%, but there are all these kind of correlations which you can remove, and it will compress the data. So this is something which also is commonly used in minimizing the resources. And now I can give a explicit definition about how do you optimize. Okay, I listed all kind of criteria for whatever has to be trade-off versus one versus the other, and there is something which I am going to call the minimal language, which means that the smallest number of building blocks has a spatial status. Of course, how many building blocks you need, it will be ultimately also depend on the type of data and whatever the task you are going to carry out. But the minimal language brings it down to as few components as possible, and that is in some sense optimization. And I have to now also I give a more explicit definition of language, which is just a collection of building blocks. How do I choose it? How do I arrange it? It is up to me. That's a part of the design. And that now allows me to construct a mathematical framework and give lot of examples from our daily experience. Okay, so I can proceed now more mathematically, and remove this stuff. So now I'm going to explicitly construct various kind of collections, building blocks, transformations, whatever you can imagine, all in this discrete picture. Okay. So how do I bring together many different components, and this depends on the, in some sense, the embedding space for all the variables. How a collection is basically how do I put things together. And I'm just going to give simple mandation definitions that zero dimension means that multiple signals at same point. Point is a zero dimension structure, and this is example of what we encounter in physics as superposition. All the signals are there together. What do you do in one dimension? It's a ordered sequence. This writing is there, it's ordered from left to right. The order matters. Even in number system it matters. When I speak, it is in time, but it matters. And it can be when not whatever. Let me write it explicitly. In physics, we can talk about some internal dimension also, where you can order things, and the mathematical label for this thing is it is considered the tensored product. It's a terminology right now. We will come to more detailed description of what tensor product is sometime later, but it's just a ordered sequence of whatever building blocks they are there, and we have lots of examples of this type. But one can go beyond. So how do I increase the dimension? Well, one way is to just look at as different dimension as Cartesian components, and one dimension is covered by ordered sequence. I have multiple ordered sequences defining in different directions. And they can do certain things which is not so immediately possible over here, because there can be correlation between these multiple sequences. So they and those correlations are another way of describing certain type of information. And easier thing is to look at very simple examples. We have 2 eyes and 2 ears. One would have done certain job. What does adding a second one allow us to do, which a single one cannot? So with 2 eyes, actually you can judge parallax, and that allows you to figure out the distance to an object. We need it. It's important in our living situation. We need to judge the distance. One eye would not have done that particular job, but doing the 2 eyes, and our brain does some triangulation. Okay, it happens inside. It doesn't do calculus, but it does things nevertheless in some particular fashion. So the images seen in 2 eyes are slightly different. And by comparing them, the brain does that job. It figures out how far the object is. In case of our ears, it's not the distance which is judged, but it's the direction that is judged. Some sound comes, I can turn my head to understand where it is coming from. How is it decided? Well, again the signal is coming, but here now it's not the space, it's the time which is matters. One ear receives the signal little bit in time different from the other one. Brain again does the comparison, and depending on the difference in time, it can figure out that it came from this side or that side. So there are important features. They are correlations. The signal is not present in one stream or the other, it is present in the correlations. And that extra correlation gives you some useful information. Okay. So this is the kind of thing one can do with higher dimensional structures. It's not, second dimension is not infinite here, it's just 2, but 2 is still better than 1. Okay. And these days, people who exploited this thing very heavily are the astronomers. They use fancy telescopes which are spread over areas, multiple detectors. They also have what you call long time exposures, not just a snapshot. They observe the same thing for a long period, and again that the correlation is in time, what is happening at different instances of time. You can observe and correlate them, and from that get images which we cannot imagine by looking at our eyes or anything like that. All kind of heavily what you call some kind of regularized photographs, but they picture stars and galaxies and things like that. It's just not possible without such techniques. There are all kind of things in the correlations which they are using. And it's not limited to astronomers' domain. You can think about other situations also where things of this order can be done. Can go higher. What will happen in 3 dimension? Well, this is a situation which is heavily used by the biological machinery. All reactions going around in our individual cells, they essentially occur by what is known as lock and key mechanism. So 2 molecules, if they have complementary shapes, they can stick together and carry out some reaction. If the shapes don't match, they will just scatter off. And how the shapes are decided? Where the shapes are in 3 dimensions. They literally have to look at all the positions of all atoms, whatever is involved in a 3-dimensional structure, and biological uh, experts, they have this short label for whatever happens, they just call it lock and key. A lock is a certain structure except that it is in 3 dimension, and the key is also 3 dimension. Some things work, some things don't. But it's all over the place, and the largest which we go according to our laws of physics is 4 dimensional. Can't go beyond that. It includes both space and time, and the systems we have based on that is, well, the global positioning system. It tells you where you are and what is your local time, both together. But it requires certain type of resources. So here I am just listing the possibilities, and it's not that you have to exclusively work with only one combination. You can have multiple things going on simultaneously, and I will just list 2 combinations which are important. So a combination of 0 dimension and 1 dimension is covered by all the quantum information theory, which we are going to deal with in some form or the other. It will have both superposition as well as the tensor product structure. And the other stuff, which is again a well-known combination, but which we don't understand even now, this is something at the heart of biology. There is a conversion between a 1-dimensional sequence written in the genes to the 3-dimensional structure of proteins, and it goes back and forth, and it works. We haven't yet understood how it works exactly, but it's a combination of those two, and if you want to understand, then you have to look at this kind of scenario in a particular mathematical framework. Okay. So this is,
one question here.
yes.
In 2-dimension case, you have written multiple ordered sequence. You have not written 2 ordered sequence. When it is in 2 dimension.
It can be higher dimension also if you have multiple, whatever it is. I was just dealing with 2. You can add more, and it may have go into higher dimension beyond 2 as well. Now let me come to the question of types of building blocks. And in the framework of this minimal language which I mentioned, it is related to the type of collection which you have. It's not a independent parameter, but it tells you many more things than just writing down the dimensionality. So the mathematical fact is this: that if you want to cover a certain dimensional space in terms of some units, what is the smallest structure you can use, and it's currently labeled as elemental volume, and in d-dimensional space it basically is defined by d plus 1 points. Okay. So what is it? Well, 0 is actually too special. It will just give 1 point, and I can't give any value to it except that it specifies a variable in some particular ways. But the interesting stuff starts at d equal to 1. So here there are two points, and any one-dimensional object can be covered by a segment made up of 2 points. I can put lots of two little intervals. This is a elementary component of the volume next to each other, and I can cover the whole line. And how do I describe these 2 points? Well, mathematically the structure is described by what is called a binary variable, or more explicitly it is called integers modulo 2. I need 2 points to basically cover this one-dimensional space, and this occurs in lots of different ways, and they have different physical realizations as well. So in our electrical circuit, the 2 points can be off and on. If you are talking about magnets, you can call it up and down. If you are talking about polarization, then you can call it horizontal and vertical, or you can call it left and right. Basically, they are all different descriptions of physics, and mathematically sometimes you call it 0 and 1, and some other places you will denote them as a +1 and -1, depending on the convenience. But they are the binary system, and in some sense the binary system is the minimal language for constructing one-dimensional structures.
I have a question.
Yeah.
If I have a one-dimensional object,
Yeah.
and I want to obtain its length,
Yeah.
in terms of these two variables,
Yeah.
binary variables 0 and 1, how can I do this?
That's how you write a number, no? Various digits. How long it is? 1.234 centimeter. 1.234 you can convert to binary. It's a set of digits. There's a place value system. Okay. It's actually this ordered sequence. So you take these binary variables, combine with a place value system, and you can write down any one-dimensional structure. And this is a very useful thing for lot of applications. And it turns out, I just give examples that many physical variables can all be mapped to binary thing. And does it help? And the answer is yes. Depends on what you want to do. And again, I give you a big example of our simple computers that you are using a binary system. It happens to be the minimal language as far as these building blocks are concerned. And what did you achieve by using that system? Okay. One is in the physical realization that the same binary label is used both in the CPU and in the memory. But the physical realization is different. The binary variable 0 or 1 label will remain the same. In the CPU, it is an electrical signal, off and on. Memory, it's a magnetic signal, it's up or down or whatever sitting on the hard disk. So the realization is different. Variable is the same. Why did we do that? Because electrical signals can be manipulated very fast by all kind of voltages and pulses and things like that. So you wanted a high speed in CPU. In the memory, you are not concerned with high speed, you are concerned with stability. You want that result to remain there long, even if I switch off the computer and switch it back on, it's still there. And these are the two conflicting criteria. If you can change very fast, it is going to be unstable. If you make it very stable, you can't change it very fast. But you need both. So then you go back and forth. That you do something fast, you save it, do something else, and when you need it, you come back. And the conversion, it happens that you have to construct. And the laws of electromagnetism, particularly the electromagnetic induction, allows you to go from electrical realization to magnetic realization and vice versa. Okay. So that is one part. So so the mathematical label is still the same, it's a binary variable, but the physics is different and you are exploiting it. Yeah.
So for the when you have magnetic relation in the CPU, we have the electrical. So in that the transition from memory to CPU.
Yeah.
So what is the relation?
Maxwell's law, if you have understood it in physics, it couples electrical and magnetic field. You can change one to influence the other, or more commonly what you see inside motors and dynamos, okay, where you can generate electrical current from moving something inside a magnet, or the other way around. If you pass an electrical current, the magnetic object will rotate. It's the laws of electromagnetism allows you to do this particular conversion. You have to find a mechanism to do it this at whatever the scale of the computer is, but the laws are the same. And the important point is that conversion exists in the physical laws. If it's not there, then you can't do this kind of stuff. There is another feature which is buried inside it. What did we achieve by using binary variables? Remember, when we studied addition and multiplication in primary school, we use decimal systems. And then to perform addition and multiplication, we had to memorize 10 by 10 tables. Say 5 times 7 equals 35, and so on. And then we can do the tasks of adding and multiplying numbers easily. Now look at what happens in a binary system. We have only two numbers, 0 and 1. And so we have to deal with only 2 by 2 tables. That is a drastic simplification in terms of the number of operations. And that's it. In electrical circuits, we implement the 2 by 2 tables by very simple operations. Logical and logical OR. And that takes care of everything which we need to do addition and multiplication. Now consider two-dimensional situations. Here the simplex is a triangle, and any two-dimensional surface can be covered by triangles of different shapes and sizes, and that is quite convenient for doing image processing. We can go further to d equal to 3, where the simplex is a tetrahedron. And any three-dimensional structure can be covered by gluing tetrahedra of different shapes and sizes together. This is actually how finite element analysis of structures is done. And it's a useful construction. What we can look at is that these higher dimensional structures can also be covered by putting together one-dimensional structures, say using Cartesian coordinates. So a d-dimensional structures will just require d coordinates. Each of them can be represented by a one-dimensional sequence. But one can easily see the difference that this kind of representation will require algebra that covers the structure z2 to the power d, one z2 for each coordinate. On the other hand, the simplex required only d plus 1 points. And there is a lot of difference between d plus 1 variables and 2 to the power d variables when d is large, and so the simplex is actually much more efficient. Now we can take the next step and look at various kind of transformations that can be performed with these building blocks. They depend on familiar constructions, but they can be more rigorously stated using language of group theory. Let me start with zero dimension, where, as I mentioned, the only operation was superposition. And superposition is nothing but operation of addition. Many different components are combined together by just summing up them one by one. What about one dimension? Well, that is our familiar arithmetic set of operations performed with ordered sequences of digits. They are addition and multiplication. So the capability of transformation has gone up. And actually, as I said, using the example of Cartesian coordinates, we can describe all the other more complicated operations in higher dimensions, can also in terms of addition and multiplication. But there are simpler descriptions of them, and one can look at them as well. So in two-dimensional, we have the generalization of addition, which can be called translation. The generalization of multiplication is change of scale. You basically magnify something or shrink something. But there is a new operation available, and that is rotation. It is different from translation and scale change. So yes, our list of transformations has expanded. One can continue to next step, 3 dimension. Now we have translations, scale change, but the rotations become more complex. Two-dimensional rotations were commutative. You have only one axis along which you rotate, and then the rotation angles simply add when you combine successive rotations. But in 3 dimensionals, we have different rotation axes available, 3 in particular. And these 3-dimensional rotations are not commutative. Rotations about different axes in general cannot be described as rotation added together about the individual axis. The third component generically appears. And these non-commutative rotations actually offer a more general class of transformations. Of course, as I said, these operations can be reduced to one-dimensional descriptions in terms of addition and multiplication, and we do express them sometimes using matrices. And matrices are easily described as sequence of elements in some order, and more complicated rotations can all be reduced to matrices of various types. Matrices in general don't commute, and they can take care of non-commutative calculations as well. We are actually going to use the algebra of the group SU2 quite heavily, and it is actually the algebra of three-dimensional rotations, and it has sufficiently interesting properties to be able to cover various transformations that appear in quantum computation. Now I can summarize various things which I described in the context of various types of building blocks and emphasize the features which I call minimal languages. They have various properties. The first one is they offer largest tolerance against errors. Why? Because the physical variables have certain range of values, and you separate those values into distinct sets corresponding to individual variables. The fluctuations within those non-overlapping sets are ignored. They provide protection against errors, but we can put those variables as far away as possible when the number is small. And that increases the tolerance available. The second thing which I already mentioned is the number of operations. The variables for a simplex actually are the minimal number of values in any dimension, and so the number of transformations which can be performed as various operations of them, they come down. I already pointed out the difference between 10 by 10 tables and 2 by 2 tables. When you include both these features, largest tolerance and small number of operations, it helps in miniaturization and simplification of a computer design. Why? Because when you try to miniaturize, the fluctuations increase and you would definitely benefit from a larger tolerance. Simplification occurs because the number of operations go down. And this has been the driving strategy for making computers smaller and smaller, which reduces resources in a sense, and which also makes them versatile objects which can be efficiently used in many different situations. They become portable and things of that sort. There is a extra cost in this simplification, and that is that what is called the depth of computation, it increases. You have a smaller number of operations, but you need to perform many of them together in some order to implement a particular task. And this increase in the depth of computation is an unavoidable consequence of simplification. But what happens most of the time, that the advantages of miniaturization and simplifications are large enough to be able to cover this cost in depth of computation. You can easily see that suppose I have a number and I write in a decimal system, say a number between 0 and 1000, I need 3 digits. But I want to write it in a binary system, I need 10 bits. That is the increase in the depth of computation, but it is a penalty which is tolerable. And with all these features together, we can point out the final consequence, which is that the reduced number of operations and small size of components makes the mapping between software and hardware simpler. At the lowest level of information processing, it is convenient to have as simple components as possible and as few operations as possible so they can be mapped to whatever has to be done in hardware, and the complexity of translating from one type of system to another kind of system disappears. There is no translation. There is only a direct mapping between the low level of software and the physical properties of the hardware. And this is always going to be the final step. The variety which we have at a very high level description is simplified to a small number of choices in the minimal language, and depending on what hardware is available, we implement them in reality. I have described many generic ideas in today's class. Just think about it and try to understand the details as much as possible. So that's it. My time is up for today.